Hello, this is an example of image formation using a convex mirror. So that's a convex mirror. We have said that the convex mirror has a focal length of 10 centimeters and the object is placed 10 centimeters in front of it. So even though the question asks us to draw the ray diagram at the very end, uh, but let's begin by drawing the ray diagram. So that's our optical axis. So that's a reference. And this is the direction of light. And somewhere in between is the mirror is kept, and the mirror will be represented by a straight line. That is just to get our scales correct. In reality, uh, the the mirror looks very flat when in this zoomed out image, but this is what the mirror, so this is our mirror will be having a curvature of this side. So that's an exaggerated image, and the polished side is on the is on the front. That means on this side, as I show using my cursor, and light cannot penetrate in that. So this is the optical axis, but light in principle cannot go beyond the mirror. We need a scale, so we will have 1 centimeters of about this distance. So that will be our 1 centimeter when it comes to vertical direction, but it will be 10 centimeters when it comes to horizontal direction. And the focal length we have said is somewhere here. So this is a convex mirror. Convex mirror has this feature that it is curved uh, onto the end where the light does not go. So that's your focal point, or length from the center of the mirror will be the focal length. If it is a concave mirror, it will be onto the left. So that's the basic difference between a convex mirror and a concave mirror. Two times that focal length is somewhere here, and that's actually the radius of curvature. So that's where the diagram of the mirror really doesn't match, because if this was the radius of the curvature, actual sphere will be something like this, right? So that should be the center of the sphere, radius of the curvature, or center of curvature will be the center of the sphere that the mirror is part of, and the distance from the center of the mirror to the center of curvature is the radius of curvature. So let's call that r, which is 2 times f. That is the same distance we can draw to the left, so roughly that's somewhere here. So we should make that precise when we have, if we have a ruler, and that's 2 times the focal length onto the left. I won't write that as minus f or minus 2f, just to not confuse with the notation. Remember, in a mirror, focal length is measured uh, negative in the direction of the optical axis. In fact, for a mirror, everything is measured negative in the direction of optical axis, and everything is measured positive in the direction against the optical axis. Okay. We are told that the object is kept 10 centimeters in front, so that will be 10 centimeters. If focal length is 10 centimeters, this is 10 centimeters, but it is in the front of the mirror. So let's use, and it is height is 1 centimeter, so that's somewhere here. So that's our object, and the object is represented by an arrow with its tail sitting right on the optical axis. Our goal is to find where the image is formed, and for that we go with ray. There are two rays we follow, and let me change the color here for a moment. Maybe let's take a lighter color and start from the head of the object. Pick the line. Start from the head of the object and draw a line going all the way to the center of curvature, which is the point R. I would also want it to reflect back, and before I show that, for that purpose, I start from the radius of curvature and go back. If we have a ruler and a paper, we can do that in a one single stroke. But this is a ray of light, so how exactly is it behaving? So for that purpose, I draw this again with uh, so light actually goes in this direction. It hits the mirror and it stops there, right? It cannot go anywhere further. That was just a reference line that connects the head of the object and the center of curvature. But actually, the light starts from the head of the object, reaches the mirror, which is represented by a straight line, not the actual the curved line, and then from there it returns back. Right? So that's my reflected light. So it goes in this direction and then returns back. And we need to follow that because wherever this ray meets with another ray, wherever they intersect, wherever two rays intersect, that's where an observer would say the image is. So that's our ray. So it starts from the head, goes to the mirror, pretend, or it wanted to go through the center of curvature because then it would go undeviated, but it cannot, so it actually reflects back, uh, except for the deviation being 180 degrees, otherwise it follows back along that it came. So that's ray one. So that's, if I can say, that's ray one. Follow another ray, and for that we take a parallel ray. So we start from the head again. Let's actually, since this is a reference line, so I draw this here. It goes, you go all the way straight, go parallel, and the idea is that the definition of focal point is that all parallel rays tend to go through the focal point if it can. So again, notice I'm not going all the way to the mirror because the straight line represents the mirror for drawing purposes. So that's my point, and I go through the focal point. And since I want to draw the complete line, so that's my complete. Let me emphasize what the ray is actually doing in red. So that was for geometry purposes. I wanted the reference lines. The ray actually starts from here, goes in straight, but it cannot penetrate the mirror, right? Even though I earlier said that all the parallel rays go through the focal point. No, it cannot penetrate the mirror. It reflects, and it reflects as if it is coming out of the focal point. So that's a converging and diverging mirror. A converging mirror, the light actually converges to the focal point. A diverging mirror, the convex mirror that we have here, it behaves as if all the rays that are coming parallel to the optical axis go out as if it is diverging from the focal point. So it looks like this, right? So that's your diverging ray. And that's your second ray of light. So that's ray 2. Wherever these two rays meet, that's where the image is formed, but it is clear that they actually do not meet at all going forward in this direction. But they do, if we extrapolate this, so that's again showing in red, if I extrapolate this, they do meet at this point. Right? And wherever they meet, that's where the image is formed, and that's my image. Right? That's the head of wherever the intersection is. That's my image. And I should change the color, maybe better. So that's my image. Oops. And that's your image. Clearly, before we even go and start working on the problem, You can say it's actually on the right side, or it's uh, like behind the mirror. So remember our notation. The focal length is measured positive, sorry, negative in this direction and positive in this direction. The object distance P is measured negative in this direction and positive in this direction. And image distance is measured negative direction and positive in this direction. In this case, I could have always said that all these three are positive in this, or when we come to lenses, we will see that that's a difference. This is the convex mirror, and that's a concave mirror. This is a virtual object. When the object is behind, that usually doesn't happen, but one can, using compound lens mirrors and lenses, one can actually uh, have such a situation. And this is a real object. And if the image distance comes out to be negative, then we say it's a virtual image. And this is a real image. Real and virtual is given by the point that if whether the rays of light are actually going through that point in an object, they originate from that point, and in an image, they actually converge or seem to be converging at that point. So now let's attend to the specific questions that's being asked. That's your ray diagram. So we have part A, what is the radius of curvature of the mirror? So radius of curvature of the mirror is 2 times the focal length. And focal length is 10 centimeters. So it's 20 centimeters. You can always say, to be more precise, R is with the signature because it is to the behind the lens, so it's minus 20 centimeters, because focal length is actually, so this is minus, right? Because F is minus 10 centimeters because it's a convex mirror. So column B, calculate the image distance. We have 1 over P plus 1 over Q is equal to 1 over focal length. So that's 1 over object is placed 10 centimeters in front. So it's plus 10 centimeters plus 1 over Q. That's equal to 1 over focal length is minus 10 centimeters. So that implies that 1 over Q is equal to minus 1 over 10 minus 1 over 10. So that's 2 times minus 10. Invert this out, so Q is minus 10 over 2. So Q is equal to minus 5 centimeters to 3 digits, right? And indeed, minus means it is behind, and it is, so this focal length is 10 centimeters, so it seems to be in the ray diagram also, it is coming exactly somewhere in between. That's our diagram is consistent with what we calculated. Part C, what is the magnification? So magnification is minus of image distance, which is Q, over the object distance, which is P. So it's minus of Q, which is minus 5 centimeters, divided by P object distance, which is 10 centimeters. So that's 5 over 10, so that's 0.5 to 3 centimeters. So it's not really magnified, it is diminished by half the size. And again, the size seems to suggest this. If this was 1, this seems to be half the size. Part D, is the image real or virtual? The image distance came out to be minus 5 centimeters, so it is virtual. And as it is shown in the diagram, also the image is formed behind the mirror as it is formed in a bathroom mirror, whether it's flat, and that's indeed virtual. What about whether it is inverted or upright? If from using the ray diagram, it is clear that it is upright, and we should be able to say the same thing by calculating uh, the image height, or even before that the magnification came out to be positive. Since the magnification came out to be positive, that means it was half the size but in the same direction. So since the magnification is positive, that's why we can conclude it's upright using the calculation or using the ray diagram. And or we can also, when we calculate the height of the image in F, we will get that. So let's go to F and due to that reason. And what's the F? Determine the height of the image. Magnification is equal to height of the image over height of the object. So height of the image is magnification times height of the object. Magnification is 0.500. Height of the object is 1 centimeters. I took two sig digits, so that's 0.50 centimeters. Which is again agrees with whatever we see here. Since it is positive height, that means it is upright. And finally, coming to G, the ray diagram, we did show the ray diagram here. Okay, let me stop sharing and stop the video.